recording will show up on my YouTube channel. I have a YouTube handle now. It's youtube.com/@Let'sWinChemistry. All right. And so it'll be posted on my YouTube channel tonight sometime, and my class, it'll be on our Zoom page. All right. So let's get started. Here's the copy of the supplemental information. This is what you're going to get. So to kind of break this down, this equation is the equation for a dipole moment, where we can calculate basically the magnitude vector qualities of a bond dipole. So we consider both the difference of electronegativity of the atoms involved in the bond, but we also think about the charge set, how far away the charge separation is. So we need to think about bond length as well. And then these constants are involved with calculating dipole moment within there. So that was chapter, I think, chapter 7. Versus this information is on related to chapter 9, specifically molecular orbital theory for diatomic period 2 elements. All right, so note here that there aren't the designations for the molecular orbitals aren't given, so you kind of have to know what the ordering is, but we do give you the order nonetheless, and so that is pieces of information that you can piece together there. And of course, you're given a periodic table. It just doesn't have names on it. It has the symbols, but no names. All right. So what chapter do we want to work on? Anyone? Even people on Zoom? 9? Okay. 9. All right. So what part of chapter 9? Do we want to go over VSEPR theory? So there's, I guess, 3 parts: VSEPR theory, valence bond theory, or molecular orbital theory. Okay. So actually, before we do that, let's go over Lewis structures, because basically all of chapter 9 is contingent on, can you draw an appropriate Lewis structure, right? So with Lewis structures, there is a set of 5 or 6 steps that will work every single time. Every single time it'll work if you follow the 5 or 6 steps. Do we know those steps? If you're given a molecule, let's say it was CF4. What are our 6 steps? What's the first step? The number of valence electrons. Yeah. So you inspect all of the elements that are present. So there's a carbon atom. So how many valence electrons does carbon give? 4. And then there's 4 fluorines. So how much does each, I already wrote it, fluorine give? 7. So it's 4 times 7. So I think that is 32 valence electrons. So I often put as step 2, adjust if it's an ion. I make that a separate step because I don't want you to forget it. If it's an ion, meaning it's a cation or anion, you need to adjust the valence charge number. So if this was, let's just pretend this was an anion, how would we change this valence electron count? We would add an electron, because remember, electrons are negatively charged. So an anion, add an electron. But if it was a cation, we would remove an electron from the count. All right. This is especially important because if you do this, count the valence electron thing and you get an odd number, you cannot solve the Lewis structure if it's an odd number. So if you get an odd number, recheck your valence electron count, and or check if it's an ion that you didn't adjust, because you can't solve an odd number. All right, so that's step 1 and 2. Step 3 is what is it? You draw the skeleton. Is that it? All right, the skeleton structure, that may sound simple, but you need to identify what the central atom is. How do we identify the central atom? It's usually first. If it's not first, so if it's hydrogen, it's never hydrogen. So for example, water, H2O, we know that hydrogen is not the central atom in water. What's the central atom in water? Oxygen. So it's not, if it's hydrogen, hydrogen can never be a central atom. Also, the true rule is whatever the most electropositive element is, or the least electronegative element, is this always the central atom. So that's the other rule. But typically how we write it, it's almost always the first element. So carbon is our central atom. So when we draw our skeleton structure, all right, we draw the central atom and all the bonds to the other atoms involved in the compound. The detail is that I drew bonds. So how many electrons did I have to use? 8. There are 2 for each bond. So I already used up 8 electrons. So think of these valence electrons as money, all right? And you can only place enough electrons based upon, you know, how many you start with. So I got skeleton structure. So I think step 4 is you place leftover electrons on the outer elements first. Then if you have any left over, you put them on your central atom. Only if you have leftover electrons. Don't be like me when I was in high school and I just put dots everywhere. I basically sprayed and prayed and in terms of Lewis structures. I didn't know the 6 steps. I didn't know. I just like put dots randomly. All right. And then step 6 is, I'll get to that. So let's go back to step 4. So we want to complete octets of all our outer atoms. So we have 8 already, 8 electrons so far. So you need to be cognizant of fulfilling octets and keeping track of how many you're allowed to spend. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I completed all the outer atoms octets, but do I have any leftover electrons to put on the central atom? No, I don't. So I'm done. The last thing really is to check your octets for all the atoms. All the fluorines have complete octets. And the carbon atom also has a complete octet, so it's good. So if we would have had extra electrons left over, we would put it on the central atom, but we don't have to. And so step 6 is if any element is electron deficient in terms of its octet, usually it's the central atom, you start making double bonds. All right, to make its octet, to fulfill its octet. Also in step 6, if you haven't noticed here, sometimes we also make double bonds if we want the central atom to have a 0 formal charge for the central atom. Examples is like something like sulfate, phosphate also exhibits this, where we make double bonds so we can make the central atom have a formal charge of 0. So those are 2 examples, right? So those are the 6 steps. It works every freaking time. And so this is a concept from chapter 8, but it propagates itself through chapter 9 through VSEPR theory, because we need to know the Lewis structure in order to predict electron and molecular domains. It comes back again in VSEPR theory, where we need to understand number of electron domains for hybridization, understand orbital overlap and what bond angles are created. Do we need to use it in molecular orbital theory? Not as much, but we can always compare the results of MO theory to our Lewis structures, and it's always consistent. And that's why MO theory is the highest, most advanced theory, because it agrees with all the other theories. So can someone shout out a number, a question number from chapter whatever, 9 that we want to work on? You just want me to yell at you for 2 hours? 21. Oh, I love 21. Oh, wait, no, that's 23. Dang it. I don't have good eyes. Okay. Okay, so 21. So 21 definitely is in chapter 9 arena. This is a valence bond theory type question, but it kind of overlaps with valence bond theory and VSEPR theory. All right. The question here is the 0 formal charge for the central atom for step 6. The part of step 6 is you make double bonds to make the central atom a formal charge of 0. Okay, so we'll do 21, then 22, then 23. So 21. So what is the hybridization of the carbon atoms left to right? So 1, 2, 3. So when talking about hybridization, we're talking about valence bond theory. So what I teach my students is, and I told them to say this 100 times before they went to sleep, is that the number of electron domains around your central atom equals the number of what? Not quite, not yet. Number of atoms that you, or sorry, number of atomic orbitals that you need to combine to then make hybrid orbitals. So it's the number of atomic orbitals to combine equals the number of degenerate hybrid orbitals you get out. Say that 100 times. Not right now, but like before you go to bed. So the number of electron domains around a central atom is the number of atomic orbitals you need to combine to describe the hybridization for that central atom. And it ends up being the same number of degenerate hybrid orbitals that come out. So let me explain. All right, so let's just go through that process. So this carbon on the left here has how many electron domains? 3. Yeah, so that double bond, remember, it's the same electron domain idea as Vesper theory, where the double bond, a triple bond, they all count as 1 electron domain in terms of just electron repulsion. So there's 3 electron domains there. So that means, according to our thing, how many atomic orbitals do we need to combine? 3, yes. So now we just need to choose, well, which one? So we always start with our atomic orbitals. We have an s orbital, 3 different p orientation orbitals. So if we want to combine 3 atomic orbitals, we just read left to right. So we're going to combine an s orbital and 2 p orbitals. Those are the ones we're going to combine. All right. So that means the hybridization for that central, the left carbon atom here is sp2. Because we literally combined an s orbital and then how many p orbitals? 2 of them. So I don't mean sp2, I mean sp squared, meaning there's 2 p orbitals combined there. All right. So when we hybridize, we no longer have the characteristics of the original atomic orbitals. We create a new hybrid set. How many hybrid orbitals do we get out of when we combine those atomic orbitals? 3. So we have a degenerate set of 3 hybrid orbitals that are sp2 hybridized. And then we have this leftover p orbital that's hanging out, not doing anything. We didn't touch it at all. Good? Okay. So what you see here in this picture is we started with four orbitals at the beginning. They just so happened to be atomic. We ended up with 4 orbitals at the end. All right, this has to do with linear algebra and linear combinations of the symmetries of these things. So the number you put in is always the number you get out. All right, so that's the long way. And so when we do this, when we hybridize, what's beautiful about this is that where we place the electrons gives us unpaired electrons to form the different types of bondings that we interact with. So sigma bonding, pi bonding. Now the electrons are unpaired and can participate in the idea of valence bond theory that orbitals have to overlap to create covalent bonds. So the first carbon, so that's the long way to answer this question. I feel like in high school, oftentimes teachers will just teach, oh, this is sp2, this one's sp, this one's sp2, but they don't tell you why. In college, we tell you why, even though you might not like it. I think it's beautiful. It's like the Sistine Chapel when we place the electrons and you see where those unpaired electrons are. So let's complete this. What's the hybridization of that second carbon? sp, because there's 2 electron domains. Does the double bond not count as 2 electron domains? It does not. It counts as 1. Same with the triple bond. So it's just any domain of electron density. All right, and then the last carbon here is sp2, right? And it's just counting electron domains, just like you would Vesper theory and predicting the molecular shape. All right, so let's order the bond angles from 1 to 3 in order of increasing angles. So I'm going to delete these. So what will be helpful here is if we predict the geometry of these carbon atoms. So those electron domain numbers will help us, because it's the electron domain numbers that'll help us predict how will those electron domains spread out from one another to give us our molecular shapes. So this carbon atom, the one on the left, has what molecular geometry? It has no lone pairs to consider. So we just have 3 electron domains. So that shape is trigonal planar. What about the central carbon? We have 2 electron domains. How can 2 domains get us far away from one another? A linear, yes. And then finally, the last carbon on the other side, also 3 electron domains, it's still trigonal planar. All right, great. So each of those shapes have specific ideal bond angles associated with them. The trigonal planar ideal bond angle is what? Ideal. 120, and then linear is 180, yes. So which is the largest bond angle? Even from the picture, you can tell, right? Yeah, number 2, right? 2 is the largest? Yeah. Okay, so then how can we compare 1 and 3? Will 1 and 3 have the same bond angle? At first glance, you might think yes, because didn't we say, oh wait, both of them are trigonal planar. They both have an ideal bond angle of 120, but are these ideal systems? No, those double bonds mess up things, all right? So if we had a molecule that was all identical 3 electron domains, so if it was like BF3, all right, where those 3 fluorines are identical, yes, it would adopt exactly 120 degrees. But in this case, for this carbon atom, the double bond is going to take up much more space. It's big, fat, and juicy, so it pushes the other bonds away. So bond angle 1, is it going to be greater or less than 120? It's going to be slightly less. See, if I say it like that, you will remember it. It'll be slightly less than 120. So same thing on the other side over here. So this carbon atom has a double bond on the other side. So do note where the bond angle I'm trying to indicate. So if that double bond takes up more space, is number 3, is it going to be greater than or less than 120? Slightly greater than. So we actually can completely order this in order. So the smallest bond angle is 1, then it is 3, then it is 2. Yeah, so if you did not consider deviations from ideality, you would say that 1 and 3 were the same, but they're not. They are not. So double bonds can screw up ideal bond angles. What else can screw up bond angles? Lone pairs. Yes, lone pairs are big and fluffy also, so they just take up a little bit more room. Okay. All right. Okay, so lots of stuff going on here. So how many sigma bonds are in this molecule? Oh, did you still need that? You still want that? You have the key, right? You have the key. Okay. How many sigma bonds are present in this molecule? So understand valence bond theory. Electrons are not just dots that are combining, right? It's not just dots combining to form a covalent bond. We actually want to think about what orbitals are overlapping. All right, so the idea here with sigma bonds is all single bonds are comprised of a sigma interaction, a head-on interaction. It could be between s orbitals, 2 s orbitals coming together. This is a sigma interaction, this head-on overlap. You can also have a sigma interaction between p orbitals. See how the overlap is the same here. You can also have overlap between a hybrid orbital and like an s or a p orbital. See how the overlap is this head-on fashion. All of these are sigma interactions. So all single bonds are a sigma interaction. Sometimes we need to think about where that unpaired electron is. Is it in an atomic orbital? Is it in a hybrid orbital? And I think we talk about that in the next questions. So a single bond is always comprised of a sigma interaction. A double bond is not comprised of 2 sigma interactions. That's a common misconception. It's actually the first component is sigma in nature. The second component is always pi in nature. So pi interactions are side-by-side overlaps. And in this class, they can only be produced by unhybridized p orbitals. Only. That's the only way you can get a pi interaction is between 2 adjacent p orbitals. 2 adjacent unhybridized p orbitals, actually, to be specific. And then following that trend, a triple bond is a sigma, a pi, and another pi. So with that in mind, we just take inventory of all of the bonds in our molecule. So I like to highlight things. So I'll just go through. Okay, there's a sigma bond 1, 2, 3, 4. So those are all the single bonds or sigma bonds. But then we also have double bonds to take into account. But the double bonds, do they give sigma components? Do they have a sigma component? Yes, they do. Just the first part. So 5, 6. So there are 6 sigma bonds. Yeah? All right. What? I don't have the second component of the double bond accounted for. So 1, 2, what are those components? Pi, yeah. So pi interactions on different between different bonds. All right, so there's 2 pi interactions here. So yeah, 2 pi, 6 sigma. All right, how many total unhybridized p orbitals are required to form this entire molecule? Yeah, you can do this. Yeah, you just did it in office hours. Yeah, it's 4. Yeah, okay, so the answer here is 4. It sounds like a tough question, right? We went from sigma, pi interactions. Now we made a left turn to p orbitals. But remember what I said. How do you make a pi interaction? A pi interaction is between what orbitals? 2 p orbitals. So this is a pi interaction. 2 p orbitals are required to make a pi interaction. How many pi interactions are in this molecule? 2. So how many unhybridized p orbitals do you need? 4. Yeah, so it's 4 unhybridized p orbitals. Let me show you something. Let's go back. Let's go back up here. What's the hybridization of that first carbon? sp2. The next one? sp, then the next one? sp2. Okay, how many total p orbitals are up here? 1, 2, 3, 4, 5. There's 5? 5 p orbitals up there? Okay. So every carbon has how many p orbitals? How many orientations are there on a p orbital? Sorry, not a p orbital, a p subshell. 3. Yeah, when you talk about a p subshell, you draw 3 boxes. So doesn't each carbon atom have 3 boxes? All right, so each carbon has 3 p orbitals. So how many total p orbitals are coming from carbons? 3 times 3 is 9. Okay, so we have 9 p orbitals to work with. We used 5 of them to hybridize. That means how many unhybridized p orbitals are left over? 4. It's right there. Isn't that beautiful? No? All right. Okay. All right, so let's just keep going. All right, 22. So remember, valence bond theory considers what orbitals are overlapping to make these interactions. So 22, why is it not necessary to use hybrid orbitals to describe the bonding in HCl using valence bond theory? So how I think of this is draw the Lewis structure first, all right? So HCl looks something like this, so like HCl, something like that, okay? If we take it a step back and we think about it, the H atom has 1 unpaired electron. Chlorine also has 1 unpaired electron. If this was like a Lewis structure, we would just say, oh, look, those dots combine, that's what makes the single bond, right? That's what Lewis theory says. Okay, but this isn't Lewis theory. This is valence bond theory. We want to think about what orbitals are overlapping in space to form that covalent bond. Electrons are not dots. They have wave functions. They exist in orbitals. We talk about them in s, p orbitals, those things. So we need to consider that. So thinking about the electron on hydrogen, what orbital is that unpaired electron in? 1s. How do we know that? Yeah, it's an electron configuration. Hydrogen only has 1 electron. It's in a 1s orbital. So that's what the electron on hydrogen looks like. So we do the same thing for chlorine. So it might help if you write out the electron configuration for chlorine. It's, is it 3? Yeah, okay, 3s2, 3p5. So if you draw the electron diagram, where is the unpaired electron? What orbital is the unpaired electron in? It's in a p orbital. So think about how an s orbital and a p orbital can overlap in space. You have one unpaired electron in a p orbital on chlorine, and it's getting close to a unpaired electron on hydrogen. What is that? What is this? That's a sigma bond. Okay, that's a single bond as well, remember, because a single bond is a sigma interaction. So when I do this, when I bring together an s orbital on hydrogen and a p orbital on chlorine, what kind of shape do those atoms make? What's the shape of that molecule right here? If I draw that bond, it's linear. It's linear, right? Two dots always make a line. Yeah. Is that consistent with the Lewis structure and the what Vesper theory would predict HCl would make? Yes. So that's the beauty of valence bond theory. It not only considers the orbitals that are involved in overlap, but it's consistent with Vesper theory. All right. So an s orbital and a p orbital can absolutely make a linear molecule. So that's why this is still valence bond theory, but we don't have to hybridize yet, because the shapes are consistent with just using pure atomic orbitals. That's A-okay. We don't have to hybridize, okay? So, the question here, what two orbitals are involved in the, so this is how this question would be worded on an exam. It would say, according to valence bond theory, what two orbitals make the sigma interaction in HCl? Doesn't that sound real hard? That sounds real hard. Yes, but you already know the answer. It's right in front of you right here. All you have to do is locate the sigma interaction. It's right here, right? It's the overlap between those two orbitals, right? Right there, right? Right? So all you have to do is name the two orbitals that are overlapping. That's it. This is the sigma interaction. All sigma pi interactions, they're made up of two atomic or two orbitals overlapping. So let's name those orbitals. Where is the unpaired electron on hydrogen? It's a hydrogen, 1s. And then where is the unpaired electron on chlorine? Not 2p, it's technically 3p. If it was fluorine, it would be 2p. Yeah. Again, because we're talking about valence electrons. Yes. Doesn't that sound so much harder? But you already know it. You already know it. It's right there. Okay. All right. Okay. So what kind of bonding interaction is HCl? Is this? Did we just draw? We already know it. It's sigma. Yes. There is no such thing as pi star and sigma star in valence bond theory. That's only an MO theory. All right. The stars, because stars mean anti-bonding. That's a wave nature of electrons. Okay. So those are valence bond theory examples that only need atomic orbitals. Only need atomic orbitals. So S, P. Okay. So here's another question. Why must, when we draw methane, 4 electron domains, right? Why must carbon hybridize? Think about it. What's the shape of carbon in methane? Tetrahedral, right? That's what valence bond theory says. 4 electron domains, 0 pairs, 0 lone pairs. It's tetrahedral. Do we have any atomic orbital? Oh, sorry. What's the bond angles in a tetrahedral? 109.5. Do you know any bond angle, or sorry, any atomic orbitals that are 109.5 degrees away from one another? If you think about s orbitals, p orbitals, right? They're just the XYZ axis. They're all just 90 degrees from one another. We don't have the correct shapes and overlap to be consistent with these new Vesper theory shapes, trigonal planar, tetrahedral, all of those. So we need to come up with new shapes. And how we do that is through hybridization. All right. But I feel like the theory and the concept behind hybridization is harder than just looking at carbon saying, okay, it has 4 electron domains. So what hybridization is it? sp3, because we have to combine 4 atomic orbitals here. So if you count s and 3 p's, that's 4 atomic orbitals. How many hybrid orbitals do we get out? 4. So when we draw those hybrid orbitals, we have 4 boxes. I don't want to, 4 boxes, right? They're all sp3 hybridized. And the beauty here is that sp3 hybrid orbitals are all 109.5 degrees away from one another. If you do the linear combination, you inspect the symmetry, that's what you'll get out when you combine those 4 orbitals. It becomes consistent with VSEPR theory. All right, so we have 4 boxes. So the beauty here is now we can rearrange the electrons on the carbon atom into the new hybrid orbitals we have. We're just rearranging the orbitals. So how many valence electrons are in carbon? 4, yeah. So 1, 2, 3, 4. So remember, in valence bond theory, it's unpaired electrons are what form covalent bonds. So based upon the picture I just drew of hybrid orbitals, how many bonds can I make to this carbon? 4, because there are 4 unpaired electrons. Let's just go back real quick to the atomic orbitals on carbon. Isn't a carbon atom 2s2, 2p2? So it's 1, 2, 3, 4 on the carbon atom. If we just look at atomic orbitals, based upon this picture, how many covalent bonds, how many single bonds can a carbon atom make? Only 2. There's only 2 unpaired electrons. And the really weird thing is that this is like px, py, pz. Those 2 electrons are 90 degrees away from one another. That's not the bond angle we want to make. That's why we need to hybridize. We have to make these new shapes to accommodate put those electrons, spread them out so they're consistent with the shapes of VSEPR theory. Okay, so is that picture consistent with the Lewis structure? Yeah, each of those unpaired electrons in the sp2 hybrids are going to make a covalent bond with a hydrogen. Each of them, each of them. Each of these interactions is a sigma interaction. It just so happens to be between an sp3 hybrid orbital that kind of looks like that and an s orbital on hydrogen. So this is the overlap right there. And then what kind of overlap is that? Sigma, yes. All right, hybrid orbitals always make sigma interactions, always. It's only unhybridized p orbitals make pi interactions. All right, oh, I need to answer this question. According to valence bond theory, what 2 orbitals make up the sigma interaction in CH4? Yeah, so we're describing this sigma interaction. On one side, we have what orbital? We have the carbons, what? sp3, what's on the other side? A 1s on hydrogen. Those are the 2 orbitals involved in the sigma interaction in that molecule. And it happens 4 times, 4 times. Cool? Yes, yes. And so valence bond theory is great because it works to describe a lot of different things. So I like to show the example NH3. So just like CH4, if you draw the Lewis structure for NH3, it looks like this. So how many electron domains are around nitrogen? 4. So what's its hybridization? sp. So 4 electron domains combine 4 atomic orbitals. So it's sp3. So when you draw out the hybrids, how many boxes are you going to draw all smushed together? 4. So 4 of them. Okay. So it's just like carbon. The carbon in CH4, right? 4 electron domains. The only difference is how many valence electrons are on nitrogen? 5. So we just put the electrons in those new hybrids. 1, 2, 3, 4, 5. So based upon that picture and the unpaired electrons, how many single sigma bonds can that nitrogen atom make? 3. Is that consistent with the Lewis structure? Yes, it is. So there, that lone pair is going to go with that hydrogen. There we go. There we go. Then what the heck is this? There's the lone pair. There's the lone pair on the nitrogen. And it's all consistent with the shape of ammonia, which is the electron geometry is tetrahedral, right? But one of those sites is a lone pair, so you cover it up. And so you have trigonal pyramid at the end. Okay. All right. So how would my answer to F and E, it should be F and E, change if the molecule was CCl4 instead? How would it change? How would the orbitals overlap? Would carbon still be sp3? Let's just draw it. So CCl4. So CCl4 would look something like this. All right. And then each chlorine, we'd have a bunch, just fill them all in. All right. So we need to ask ourselves what orbitals do those unpaired electrons originate from? So to just answer this quickly, that carbon is actually still sp3 hybridized because there's still 4 electron domains. But where is the unpaired electron on chlorine? Is it in an s orbital anymore? No, it's in what kind of orbital? It's in a p orbital, specifically a 3p orbital. Is that still consistent with valence bond theory? Can we still get sigma bonding with a p orbital and a hybrid orbital? Yes, we can. Yeah, so I'll just erase this one. So here we have hydrogen's s orbital. The overlap I can get with a p orbital would look something like this. All right. See, look, sigma bond, boom. Hybrid or we don't have to hybridize on chlorine here because its unpaired electron is in a p orbital that's consistent with what the kind of bond we want to make in this molecule. Okay. So, okay, let's do 23. So here I give you the hybrid orbital set. Where's my chapstick? Oh, it's in my pocket. No. So I give you the hybrid orbital set. Dang it. And we need to figure out which atom it's referring to. So to break this down, the details I want you to note is what kind of hybrid orbital set is it trying to describe right now? Like, what are these things? 1s, sp2, 2p. I want you to hone in on sp2, that hybridization, because now we're working backwards. If I tell you the hybridization, if I tell you it's sp2, how many atomic orbitals did you need to combine? 3. How many electron domains are there? 4? 3, yes, 3 electron domains. So we're looking for an atom with 3 electron domains. So we can probably eliminate most of these, right? So does 1 have 3 electron domains? No, we can eliminate that. What about, so I didn't actually draw in the lone pairs here, so I'll just draw them in real quick. So this oxygen has 2 lone pairs. This oxygen also has 2 lone pairs. So this oxygen, it does have 3 electron domains, so we'll skip it for now. But what about this oxygen? No, it has 4 electron domains, so we can eliminate that. What about this carbon? It has 3. So we're considering 2 and 4 right now. So if we look closely here, let's just look at the valence electrons. Those are these are the valence electrons. So we actually can ignore the 1s because that's inner electrons. How many valence electrons are spread out here? 4. What atom has 4 valence electrons? Carbon, yes, so that's the answer. But let's go a little bit deeper. And I want to prove to you that this is carbon. Prove to you it's carbon. So I'll erase some of this stuff. So it's sp2. So it's indicating 3 electron domains, carbon. There's 3 unpaired electrons in sp2 hybrids. So how many sigma interactions can this atom, can this atom make? 3. Look at this carbon atom. How many sigma interactions is it making? 3. There's 1 right here. There's 1 right there. And there's 1 right there. How many pi interactions is that carbon making? 1 right there. Let's go back to the picture. There's 3 unpaired electrons in sp2 hybrids. Okay, those are making the sigma interactions. This 1 electron is doing what? It's making the pi interaction with the other oxygen. All right, and so that's consistent with everything we see. For fun, let's draw what the orbital diagram would look like for oxygen. So let's look at this oxygen. How many electron domains? 3. So how many atomic orbitals do we combine? 3. So what's its hybridization? sp2. So how many hybrid orbitals do you draw all blocked together? 3 of them. 1, 2, 3. So it's sp2 hybrid, but what do I not have drawn? The 2p unhybridized orbital left over, right? Yes. Okay, so how many valence electrons does oxygen have? 6. So 1, 2, 3, 4, 5, 6. Sigma interactions come from hybrid orbitals. How many sigma interactions can I make here? 1. How many sigma interactions does that oxygen make? 1. How many lone pairs does it have? How many lone pairs are here? 2. How many pi interactions can this oxygen make? 1. How many pi interactions are on that oxygen? 1. Beautiful. Beautiful. Do you not think it's beautiful? You do? Okay. Whisper, whisper, whisper. Okay, what else? So the question here on chat says, shouldn't Cl be 2p, not 3p? No, so remember, it's only valence electrons that are participating in chemical bonding. So the unpaired electron is in the valence shell, which happens to be in the 3p orbital. But if this was fluorine, it would be 2p. Okay, other questions? Numbers? Okay, then I'm just gonna do 11. What do you want? What do you want? Okay, all right. Wait, 9 and 11. Let's do 9 real quick. Okay, so 9, what substance is predicted to be most acidic? So this is throwback to chapter 7, where we looked at different properties and different measurements, ionization energy, electron affinity, and how the trends on the periodic table work, and how our N value for valence electrons relates to Z effective, and our trends for either removing or adding electrons. So attached to that chapter is trends on the periodic table of non-metallic versus metallic substances. I like to just memorize, okay, here's my crappy periodic table, that cesium is the most metallic element, cesium. And then fluorine is the most non-metallic element. And that will get you far in life, because when we think about oxides, all right, metal oxides are basic and non-metal oxides are acidic, where the more metallic the metal, the more basic. The more non-metallic the non-metal, the more acidic. So if this question is asking what substance is the most acidic, what is it actually asking? Which element is the most non-metallic? That's what this question is asking. That's it. So you're going to look for the element that is closest to fluorine, which is which one? Sulfur, yes. But let's check it out for ourselves, because I like to do. Then which element, which oxide is the most basic for fun? Potassium oxide, yes. All right, let's look at the acidic ones. So phosphorus, sulfur, and carbon are all going to be acidic, but sulfur is the most acidic. So when we have a phosphorus containing oxide, I'll just call it POX, we get H3PO4 in water. When you dissolve an oxide of phosphorus in water, you get H3PO4. When you, oh, that doesn't look good, dissolve that into water, you get H2CO3, carbonic acid. When you dissolve SOx into water, you get H2SO4. Do you remember our strong acid rules, our 7 strong acids? Which one of these is on the 7 strong acids list? Sulfuric acid. Is carbonic acid or phosphoric acid strong acids? No, they are weak acids, so they are less acidic. And is that consistent with our answer? Yes, it is. Okay, so that's how you do that question. All right, so the question was 11. So let's do 10, then do 11, because they're related. So lattice energy, there's 2 types of questions we can ask you relating to lattice energy. So this is energetics of ionic compounds, all right? So metal plus non-metal, right, forms ionic compounds. You know, chapters, all of chapter 9, it's all covalent compounds, right? So 2 non-metals coming together. So this is us addressing the energetics of ionic compounds. So we have, you know, cations and anions coming together. So when I draw a cation and anion coming together, is that repulsions or attractions in terms of potential energy? Attractions, yes. So lattice energy actually trends exactly with potential energy. So if you remember Q1, Q2 over D, our favorite, all right, it'll help you. Because how we predict magnitudes of lattice energy is that the more Q1, Q2 attractions there are, the higher the lattice energy. Lattice energy, it's the energy to rip apart ions from the solid into the gas phase. So if we have a +3, -3, it's going to be real hard to separate them versus a +1, -1 type of attraction. So you always consider Q1, Q2 first. If Q1, Q2 is the same for a substance, then you look at size. So the idea is if you have 2 ions, if they're close together versus far apart, which one is harder to separate, when they're close or when they're far? When they're close. So if you have any substances with the same Q1, Q2, you look at size. And that's how you differentiate which one has the higher lattice energy. So let's do it. So how I do it is I just go through and calculate the Q1, Q2 product. So we have +1, -1, +2, -1. So even though there's 2 chlorines, just look at the charge of one of them. Then we have +2, -2, and then we have +1, -1. So which one of these is hardest of ions is hardest to separate? Magnesium oxide, because its Q1, Q2 product has the largest magnitude. So we can straight off the bat say that one is the most. Then what's second? MgCl2, yes. So last is sodium iodide and sodium chloride, but their Q1, Q2 is the same. I know they're the least, but I need to figure out the ordering here. So now that we arranged via Q1, Q2, now we look at size. So see how sodiums are this, so we're comparing NaI and NaCl. So the NAs are the same, the sodiums are the same, right? Same size, but where it differs is the anion. Which anion is bigger? Iodide is bigger. So I- is bigger than Cl-. So does that make the lattice energy of NaI bigger or smaller? Smaller, yeah. So it's going to be NaI, then it's going to be NaCl. So basically, the strategy here for lattice energy questions is you look at Q and Q2 first, then you look at size. That's it. Okay, so that's how you do it conceptually. We can also do the Born-Haber cycle where we do it quantitatively. So lattice energy is related to one of the steps on this diagram. Lattice energy is why ionic compounds form at all. It's why they form at all. Because we get a lot of energy back when we bring cations and anions close together. We get a ton of energy back, and it's really thermodynamically favorable. So all Born-Haber cycles are built basically the same. What you want to look for and reference yourself to is this H1 step. This first step that's kind of pointing down, where we're taking elements in their standard state or most stable state and forming the salt. This is the enthalpy of formation of your salt, of calcium chloride. That's what you want to reference yourself to, because the whole idea is we're going to take the elements in their most stable state and just take a different way to get to the salt. And by doing that, we can calculate lattice energy. So delta H7, this seventh step, the absolute value of that is actually the same lattice energy that we qualitatively calculated in the previous question. So basically, bigger arrow, bigger downward arrow here means bigger lattice energy, that you get way more energy back when the charges of your cation and anion are large, or when your cation and your cation or anion is small. The downward arrow is larger. All right. So delta H1 is the formation step. So if we kind of look really closely of what's changing, this second step, we're turning calcium solid to calcium gas. What is that? That's called sublimation. Let's see what's happening in the next step. Calcium staying the same. What we note here, we're taking a chlorine molecule, turning it into 2 chlorine atoms. What are we doing? We're breaking a chlorine bond. So that is the bond enthalpy or bond dissociation enthalpy of diatomic chlorine. Okay, what's the next step? What are we doing in the fourth step? Ionization energy. We're taking that calcium gas particle and we're ripping an electron off of it. It's the ionization energy. Specifically, which ionization energy is it? It's the first one. Yeah, so this is the first ionization energy of calcium. First ionization energy. Okay. Why did we have to, because the question is, students are like, well, why do we have to do the sublimation step? If you remember back in chapter 7, ionization energies, they're all measured, removing an electron from an atom in the gaseous state. So that's why we have to sublimate calcium solid first. Okay, but that means chlorine is already in the gas phase, which is nice. So, oh wait, we're not at that step yet. Okay, so what's delta H5? The second ionization energy, where we're taking calcium plus, okay, because we're taking off the second electron. So it's the second step that we're doing here, a second ionization energy. We're ripping that second electron off. Okay. Yes. So now we have 2 chlorines already in the gas phase. So now those chlorines are going to gain an electron each. So delta H6 is the electron affinity of chlorine. It's actually ×2 because there's 2 chlorine atoms there. Also, I might have made up these numbers. I'm not sure if they're right. It's hard to write questions like this. Okay. So what you see here, the result here after all of those steps is we have calcium plus in the gas phase. We have chloride minus in the gas phase, right? They're anions and cations. The thing is that salt doesn't exist in the gas phase. So we need to bring those ions close together into the solid phase. In doing that, it releases a ton of energy because of potential energy. If you think about our potential energy curve, we're going from the particles being really far apart to being really close together. So we have this huge downward motion, all right, downward of potential energy. And so that means energy is released in terms of an exothermic reaction. Okay, so that's what all of the steps mean. And so it's the absolute value, or so delta H7 is a exothermic process. We get this energy back. But the thing is, in the previous question, we usually report lattice energy in terms of magnitude. So I want to compare, okay, how big are these arrows in different substances. So CaCl2, calcium chloride, is going to have a smaller lattice energy than something like calcium oxide because of the charges. So basically, calcium oxide will have a larger, further drop for delta H7, you know, in its own Born-Haber cycle problem. All right. So that's each step. And doing that gets us back to the starting point of making the salt. So what is the lattice energy of calcium chloride given this stuff? So how I do it is you can just use geometry. You just need to figure out how big this arrow is. That's it. You just need to figure out how big that arrow is. You can use like geometry and like rectangles to help you. Okay. Basically, you know all of these lengths, right? So you can figure out what does the length of this piece have to be to make both sides equal. Or you can use my equation where the delta H of formation equals the sum of all the steps up until the lattice energy, the last step until the lattice energy step. So basically all the steps until you have the gaseous ions. So this step, okay, minus lattice energy. That's it. You take the formation step. So this first one, that first number, you add up all these steps to get to here, and then you subtract lattice energy. And then doing the subtraction of lattice energy gives you a lattice energy that is a positive value. Because I gave a question very similar to this over the summer. And I literally wrote in bolds on the question, report your answer as a positive, your lattice energy as a positive value, because lattice energy is always a positive value. Half of the students who got it wrong, do you know why they got it wrong? They gave a negative value. Yes. Okay. So don't report lattice energy as a negative value. It's always positive because of the definition. It's energy to separate a salt into its ions. So based upon all these numbers, it's going to be delta H of the first step equals delta H of the second step all the way to delta H of the sixth step. So you literally just add up all those numbers minus lattice energy, and that's what you solve for. What's the answer? I don't have my key, or it's right. I don't feel like opening it. 1,000, 2,000, 252. Okay. Okay, how's that? Good? Okay. So do realize that we could give you the missing piece to any one of these steps, but you can still solve it. So if I didn't give you like the first ionization energy, but I gave you lattice energy, you just have to fill in, you know, the right step. Great. All right, next. What's the fourth question on 20? Didn't I already do 21? Oh, we want to do 12? Yeah, we'll do 12. Let me just look at 21. I already did it, so just watch the recording. All right, so number 12. Rank these bonds in order of increasing polarity. Students will say, well, you didn't give me an electronegativity table. I can't do it. Yeah, you can. Yeah, you can. Because we know the trends. What are the trends for electronegativity? Fluorine is the most. Yeah, so fluorine is the most electronegative. What elements are also pretty high? Oxygen, nitrogen, chlorine, bromine. All of those are above an electronegativity of 3. Right? Hydrogen is weird. It's very close in electronegativity to carbon, even though it's like over by the metals. Okay. So my trick to this is usually the further away the elements are from one another, on the periodic table, the more electronegative difference between the bonds. Because if you think about it, electronegativity increases going left to right, and it decreases going down the periodic table. So if you pick two elements in a bond that are like literally far apart on the periodic table from one another, you have a metal and a non-metal. So that's going to be the most polar. So polar, it's ionic. Right. So that kind of can help you out of a jam sometimes, get you on the right track to figure out, okay, what's polar, what's more non-polar, because of these, which is the most non-polar bond? Diatomic, oxygen, oxygen. It's the most non-polar because even though we don't know the numbers, what is its delta En? 0. It has to be 0. It doesn't even matter if you don't even know the number, because it just is the same number and you'll always get 0. All right, so now our options are OS and OF. I hope I can do this. So let's get a periodic table. So let me draw a periodic table. So I have nitrogen, oxygen, fluorine. Where's sulfur? Is sulfur down here? Yeah. Okay. So we have two choices, oxygen and fluorine, or oxygen and sulfur. So Dr. N said, oh, the further the elements are apart, the more electronegative. So unfortunately, they're both one away, so that doesn't help us here. But there are some trends, and I'm trying to get the wheels in my head to turn to solve this. We need to figure out which pair is going to have the larger difference. And the trick is here, you want to think about relative electronegativities. Remember when we started the trends with electronegativity? Fluorine is the most electronegative, but what's also fairly high is oxygen, nitrogen, chlorine, and bromine. So since oxygen is fairly high, fluorine is the highest, won't the difference in electronegativity for OF be pretty small? Smaller than OS, because oxygen is fairly electronegative. Oxygen's fairly electronegative, but sulfur isn't. So in that case, OS is going to be the most polar. OF is going to be not as polar, because oxygen and fluorine are very, very highly electronegative things. Oh, the question is incorrect on my key. Is it? That's what happens when I write my own questions. Dang it. Okay. So you should just ignore 12. You can't solve it using the trends that we taught you. So you should just ignore it. Yeah. Sorry about that. This is what happens when I write my own questions. Great. So let me come up with another example. Let me come up with another example so we're satisfied here. So what if I did NO, NF, NO, NF, what else can I do? Can't do that. Okay, N. We can just do that one. Okay, so which one is the most nonpolar? NN, of course. Yes, that one is an electronegativity difference of 0. Yay. Okay. Now, NO and NF. Which one will have the higher difference? NF, because the elements are further away from one another. Yes, further away from one another. So NF is going to be more polar than NO. Let's see if I can't think of another one. I can't think of another one right now. So there you go. So there's another example that you can work with. Number what? Okay. Which figure shows the successive ionization energies for aluminum? So successive ionization energies, it's energies to remove electrons. Okay. Why do we talk about valence electrons on things? The valence electrons are always the outermost electrons. We're so concerned about valence electrons because those electrons are most likely to participate in chemical reactions because they are most easily removed. So this question is really asking, can you identify which graph, which set of data correctly represents the number of valence electrons on aluminum? So how many valence electrons are on aluminum? Three valence electrons. So if we want to represent 3 valence electrons, what are we looking for? What qualities of a graph are we looking for? 3 short, small energies, and then on the 4th ionization energy, shouldn't the energy be really large? So you're going to see a huge jump in energy for that 4th ionization energy, because now you're starting to pull out inner core electrons. Those inner core electrons have really, really high effective nuclear charges. And so it's going to be real hard to remove those attracted electrons. So we're looking for a graph with 3 low energies. So A is, it's kind of not clear how many valence electrons there are here. Maybe there's 4, I don't know, but it's not the correct graph. Graph D is showing how many valence electrons? 2. But the problem is isn't both C and D show 3 valence electrons? Yeah, but there's a problem with one of them. One is more right than the other. Actually, one of the graphs is impossible. Can't happen. So D shows 3 successive small energies and then 2 large ones. C shows 3 small ones, but what's the difference? It goes up, then down. So what this graph is trying to say is that, oh, the second ionization energy of aluminum, that this chemical reaction, Al to 2+ plus an electron, that this step is harder than this step, than this reaction, Al3+ plus an electron. So let's think about this. So this graph is trying to say that this second step is harder than this step. If we think about it, we're trying to remove an electron from something that's already positively charged. Is it easier or harder to remove an electron from something that's highly positive? It's going to be hard because it's already positively charged. So there's more attraction here. So this third energy needs to be larger. The detail here is that in successive ionization energies, it always gets harder to remove more electrons because the charge is changing. Yeah. Okay. Also, when you remove electrons, your atom gets, or your ion, your particle gets smaller, right? So that means the electrons are closer to the nucleus. It's going to take more energy to grab electrons closer to the nucleus. Okay. All right. So the answer is what? D, I think. Okay. All right. On that note, I actually want to do, we always want to do the hard questions here. Let's do some of the easy picking questions on the exam. No, because if you get these wrong, then you're going to be kicking yourself. So let's consider the size, ordering the size of these compounds, these different substances. So the strategy I use to determine size is I compare N value of valence electrons first. If the N values are the same, you calculate Z effective of the valence electrons to then further distinguish size. You want to consider ions, right? Cations are always smaller. Anions of the neutral thing, it's always bigger. And then finally, you might want to consider anything that is isoelectronic, Anything that's isoelectronic, you want to compare the number of protons in the nucleus. So let's look at these. So potassium plus the cation, if we think about the n value of its valence electrons, potassium, it loses an electron, so it becomes argon, electron configuration of argon. So that's actually n equals 3 because it lost its only n equals 4 electron versus the neutral potassium is n equals 4. So of these, you can clearly see which one's bigger. It's the neutral potassium is bigger, right? But let's keep going. Chloride, right? Chloride, we add an electron, right? Argon, so that's n equals 3. Calcium 2 plus. Calcium 2 plus is you lose 2 electrons, also becomes argon. So what's the n value of its valence electron? Also n equals 3, okay? And then rubidium neutral is n equals 5. Okay, so of these, you can clearly see which one's the biggest. It's rubidium because of the n value. All right. What's next? It's the neutral potassium because of the n value. But now we have a problem. We have 3 substances that all have n equals 3. So you might think, oh, I need to look at effective nuclear charge. Maybe. Actually, that'll help as well. But even more simply, you might be clever and see that all of these 3 elements that are left over have the same electron configuration. So they're isoelectronic. All of them have 18 electrons because they all have the argon noble gas configuration. So at this point, you can just compare, since they have the same number of electrons, just compare the number of protons in them. So we're essentially comparing the Z component, because all of them have the same shielding, essentially. So potassium has 19 protons. Chloride has how many protons? 17. Okay. And calcium has 20. So if you're a stupid electron, which one are you most attracted to? Plus 20. You're most attracted to plus 20. So that means what? Are you the biggest or the smallest? Smallest, yeah. So calcium 2 plus, next it'll be potassium plus, and then chloride minus. There we go. Good? All right. On that same vein, I want to do electron affinity because everyone messes up electron affinity. Electron affinity is typically an exothermic term, all right? We usually think about electron affinity that putting an electron on an atom is typically thermodynamically favorable because the valence shells of nonmetals have an effective nuclear charge, that there's an attraction for electrons to be added to a valence shell. So I want you to be really cognizant of the language here. Oftentimes when we think about magnitude of electron affinity, we want the most negative, most exothermic value, meaning we want the scenarios where that added electron to the atom or to the whatever is most attracted. So basically you will see more exothermic electron affinities, so more negative electron affinities. All right, so the exothermicness will increase if the added electron is highly attracted to the nucleus. And so, as always, potential energy gets us out of a jam. All right, if you remember potential energy, where we have Q1, Q2 over D. So basically, you want to think, okay, what effective nuclear charge is that electron experiencing when you're adding it? Also consider the size. So how close are you bringing that electron to your nucleus? So you want to compare N value. You also want to compare effective nuclear charge. So kind of like size. First look at N value, then look at Z effective. Also look at any changes that might happen when you form ions, and there's electron repulsions taking into account. All right, so let's look at the first one, oxygen and fluorine. So I usually look at the N values first. Both of them are N equals 2. So we can kind of ignore that. So after n equals 2, it's the same. Let's look at Z effective. Oxygen for its valence electrons has what effective nuclear charge? Oh yeah, what's the trick for effective nuclear charge of valence electrons? It's just group number. So a oxygen will have a +6 effective nuclear charge on its valence shell, and a fluorine will have a +7 effective nuclear charge. Do you remember how to calculate effective nuclear charge? You guys said that chapter 7 was the easy one. No, you don't remember? You said that this was the easy chapter. All right, then let's do number 2. Let's compare the effective nuclear charge of a valence electron on sulfur. Okay, I can't do the hard question until you get the easy stuff, like this question. Let's compare the effective nuclear charge of a valence electron to the effective nuclear charge of a 2s electron on sulfur. So what will often be helpful is if you write out the full electron configuration, right, of the thing. So 1s2, 2s2, 2p6, 3s2, 3p, can I stop yet? Yes, 3p5. Okay, great. Those are all my electrons on a sulfur atom. How many protons does a sulfur atom have? 16. So all of these electrons are orbiting this +16 nucleus, all right? They're all looking in to that +16. +16 is Z, because the equation for Z effective is Z minus S. So for all of these equations, whether it's a valence electron or 2s electron, Z is +16. All of the electrons are looking at a +16 nucleus. So we need to consider shielding depending on what kind of electron we're focusing on. So, oh yeah, it's P4, sorry. Thank you. So let's look at a valence electron first. So our valence electrons are in what n level? 3. Yeah, so we're here. We're right here. We're these electrons. It doesn't matter if we're a 3s electron, a 3p electron, it doesn't matter. We're sitting in this third row, okay? We're at Taylor Swift concert. She's +16. We are sitting in the third row. We're looking in to the stage. How many electrons are between me, n equals 3, and Taylor Swift? 10. There are 10 electrons there. So my shielding is 10. So for a valence electron, all right, so like 3s, 3p, Z is 16. So it's 16 minus shielding, which we just calculated is 10. There's 10 people sitting in front of me. All right, what's left? +6. So that means those valence electrons actually they don't experience the full radiance of Taylor Swift. There's 10 people standing between their row. There's 10 electrons standing there. And so they only actually feel a +6. And so that +6 also just so happens to be sulfur's group number. So based upon that idea, what is the effective nuclear charge of a valence electron on oxygen? Also +6. What about the valence electron on a chlorine? +7. Okay, good. Those are only for valence electrons, because you see the second part of this question is what is the effective nuclear charge of a 2s electron? We can't use the same trick because it's not a valence electron, but we can still use the same analogy. All right. So we are not sitting in the third row. Where are we sitting if we're a 2s electron? We're in the second row. We're sitting right here. We're right there. So if we look into the concert, how many electrons are standing in front of me? 2. So shielding is 2. Oh, I love that. So what is the effective nuclear charge of that 2s electron? Yeah, so you do 16 minus 2, it's +14. So what we see here is that inner core electrons experience a higher effective nuclear charge because there's less shielding involved. All right. So which electron is more attracted to the nucleus, a 3s electron or a 2s electron? 2s is way more attracted. So which one do you think is harder to remove? That 2s electron. So do you ever think we'll remove that 2s electron? No, it's real attracted, versus the valence electron experiences a much, much lower effective nuclear charge. And so that's why those valence electrons participate in chemical reactions. Oh, and then finally, which electron is predicted to be closer to the nucleus? So same idea, which one's more attracted? The 2s electron. So that one is going to be closer to the nucleus, and that's consistent with the Bohr model. All right, so now with that in mind, Z effective. Oh, let's do this one. Let's do 3. Which of the following atomic radius comparisons is explained by a difference in Z effective of valence electrons? Because essentially what you're doing when you're predicting size of atoms, you're looking at N, you're looking at effective nuclear charge if N is the same. You're looking at ions like added or removed electron repulsions with those. So all of these options are correct. Yes, fluoride is larger than a fluorine atom. Arsenic is larger than phosphorus, but we want to choose the one that is explained by a difference of effective nuclear charge. So let's just go through these and state why the trend is the way it is. Why is fluoride, the anion, larger than fluorine? There's more electrons. There's more electrons, so there's added electron repulsion. Why is arsenic larger than phosphorus? Look at it on the periodic table. Arsenic is N equals something, 2, 3, 4. Phosphorus is N equals 3. So N equals 4 is further from the nucleus according to the Bohr model. So that's why that one, so it's N values here is the reason for B. So not what we're looking for. I'm saying argon is bigger than neon. For what reason? N value again, because the Z effective is the same for both of them. And then finally, sulfur and chlorine. This one is explained by Z effective because both of them are actually N equals 3. Yeah. Sulfur is +6 of its valence electrons at Z effective. Chlorine is +7. So if you're a stupid little electron, are you more attracted to a +6 or a +7? +7. So you're going to be closer to the nucleus. You're going to be smaller. Okay. Great. So I think the answer is D. All right. All right. So let's finally go back to 6. Which of these is most favorable? If you're an electron, you're negatively charged, are you going to be more attracted to a +6 or a +7? Plus what? Plus what? 7, yes. So adding an electron to fluorine is going to be, fluorine is going to be more favorable, all right? So this one is going to have the more negative electron affinity. We're thinking about, energy we get back when we add that electron. So you want to think which one has more attractions. All right. What about oxygen and O-? Oh, they're both oxygen. They're both +6 Z effective. How do I tell the difference? What's the difference here? One is a neutral atom. The other one is an anion. So trying to add another electron to something that is negative, already negatively charged, that's not favorable. All right. So think about, again, like put your monkey brain on and think you're just a negative electron. You want to think, are you attracted or are you repulsed by this? So this electron feels a little bit of repulsion to this anion, but but if you think about adding an electron to this oxygen, there's less repulsions because it's not an anion. It's neutral and it has an effective nuclear charge of +6. So which one's more favorable to add an electron? The neutral or the anion? Neutral, yay. All right, sulfur and selenium. Look at them in the periodic table. They have the same Z effective, but what's different about them? N value, all right? So their N values are different. So if you see that, just think about size. Think about the size. Both of them have the same effective nuclear charge. They're both +6. All right, they're both +6, but the problem, the difference, the differentiating fact here is the size. Which atom is bigger? Selenium is larger. So think about it. If you're an electron, are you going to be more attracted when you're far away from the nucleus or close to the nucleus? Close, all right? So it's going to be more favorable to put that added electron close to the nucleus, all right? So the answer here is sulfur, that you'll get more energy back if you add the electron closer to the nucleus. And again, all of this stems from potential energy. Q1, Q2 comes from Z effective over D. We see that potential energy decreases, at least in terms of attractions. All right, we get more negative when we have high charges, so like high attractions, or we have we bring that electron really, really close to the nucleus. All right, and the last one. So cations and anions always screw us up. So we have potassium and potassium plus. What does your monkey brain say is you have more attractions? Yeah, potassium plus. And that's the right answer. You get more energy back if you put the electron on the cation because it's already positively charged. All right. How I got -2. I'm not sure what that's referring to. Okay, what's next? 5. Oh, okay. So we want to do 5. We're on the same trend. All of these have to do with N, Z effective, electron repulsions, all those sorts of things. So 5 says, which of the following possesses the larger ionization energy? Let's bring it back, folks. I don't want to yell all night. The larger ionization energy. So we're looking for which substance is it harder to remove that electron. Again, it all comes to potential energy. That electron is hard to remove if it's close to the nucleus. So you look at N value. That electron is going to be hard to remove if it experiences a large attraction or a large Z effective. And then finally, you might have to consider repulsions that are added or removed if we're talking about cations and anions. So let's look at potassium and calcium. Look at them on the periodic table, locate them. All right, so potassium and calcium, they're in the same N value, but how do they differ? Z effective, yeah, they're effective nuclear charge. So calcium has a +2 Z effective, all right, +2, so Zeph. Potassium is +1. So in which scenario is the electron more attracted? +1 or +2? Are you more attracted to a +1 or +2? +2, so is it gonna be easier or harder to remove you from when you're more attracted? It's going to be harder. And so that's equates to a larger ionization energy. All right. Okay. What about potassium, rubidium? These both have +1 Z effectives for their valence electrons, but how do they differ? N value. So we're going to just look at the lower N value here. So the answer is potassium because that electron is just closer to the nucleus. All right. Sulfur and phosphorus. They're in the same N. They're in the same N value. Oh, but this is one of our exceptions. So they're in the same N value. They're N equals 3 or whatever. So sulfur is, if you look at its valence shell, we're removing an electron. So it's 3p4 of them. So, right? Yeah. So 1, 2, 3, 4 versus phosphorus. So that's sulfur. Versus phosphorus is 3p3. So there are the 3 unpaired electrons in phosphorus. So which of these is easier to remove? Phosphorus? So think about it. You are a coach on a dancing team, all right? The electrons are your dancers. Who's making the cut first? All right, your electrons are dancing. If you're looking at this picture, is there an easy cut and dry player or person that you're cutting from the team? Yes, the one that is dancing the wrong way. Versus, what about over here? Is there any obvious place to make the cuts of the team? No. So it's actually easiest to remove this electron. So this is anomalous, all right? It's one of our exceptions. If you look at sulfur, it's +6. Phosphorus is +5. So you would think, oh, it's harder to remove a valence electron from sulfur, but it actually ends up, it's slightly easier than for phosphorus because of this pairing effect. All right, so it's actually slightly easier to remove that electron from sulfur because it's spinning the wrong way. Okay, so our answer, I think, here is phosphorus, and it's an exception. So you see it for, the exceptions are for 2A and 3A elements, and then you see it again for 5A and 6A elements. It's a site switching. So you can't just use like, oh, fluorine is small. It has the highest Z effective. Cesium is really big and a low Z effective. It has the lowest ionization energy. You can't use that trend because there are some anomalous ones in the middle. All right. Next, okay. Removing an electron from K or K+. Yes, it's going to be much harder to remove an electron from K+ because it's already positively charged. Okay. Chlorine or chlorine minus? Which one's harder to remove an electron? Which one is harder to remove an electron? Chlorine or chlorine minus? It's like halvesies. Yeah, so it's actually chlorine. Yes, it's chlorine. The reasoning here is chloride is already negatively charged. It's already negatively charged, so you get like an extra boost because you're removing like a negative electron, right? So there's a little bit of extra repulsion. Also, actually, another reason is which atom is bigger or which particle is bigger? The Cl minus. So is it easy or hard to remove an electron that's far away? It's easy. So for chlorine neutral, the electron is closer to the nucleus, so it's harder to remove. That's another reason. Okay. You have 25 minutes. What do you want to do? Okay. All right. All right. So for 26, we left valence bond theory, going on to MO theory, but we still want to use the ideas of bonding interactions. So sigma interactions versus pi interactions. So what we want to recognize is what these pictures are depicting are different molecular orbitals. Molecular orbitals, all right, and MO is always comprised of two atomic orbitals. So we can determine what kind of atomic orbitals are being combined. They could be s orbitals, they could be p orbitals, all right? Also, this is specific to MO diagrams, we can also have bonding orbitals, so like sigma or pi, or we could have anti-bonding orbitals, so sigma star, pi star. So anti-bonding orbitals, again, remember, MO theory is we're considering the wave function. We're considering electrons as being waves. Waves can add constructively and destructively. We're bouncing off of valence bond theory. We're not only thinking about how do these orbitals overlap. So like, for example, if I draw these two s orbitals, all right, what kind of interaction is this? Sigma, yes, sigma. But now, all right, so that's the valence bond picture, that orbitals are overlapping. But in MO theory, we also need to consider the wave nature. What if the phasing matches? What if the phasing of the two waves matches are in phase, would you get constructive or deconstructive interference? Constructive. So if the phasing matches, we get a bonding orbital. So it's specifically sigma bonding. So it's lower in energy on this diagram, what you see right here. So for example, what we see in this diagram here, on the ends, we have our atomic orbitals for our atoms. So these are our S atomic orbitals. Here are our P atomic orbitals. In the middle, and only in the middle, we have our molecular orbitals. Molecular orbitals are always comprised of 2 atomic orbitals. So these are where our sigmas or pi stars, that's where they live. So from this diagram, this is exactly what you'll get on the exam. We don't give you the MO interactions. You just need to memorize them. So I'm not going to go through all of the specifics, but it's sigma, sigma star. Then what is this interaction right here? Sigma. How do we know that? Because it's the 1. Because the next one is what? Pi. Yes, because pi's always come in pairs. So then what's this pair? It's not pi again. It's pi star. And then it's sigma star. So if you just memorize that, you will probably still get this question, right? Or similar questions where you have to add electrons to diagrams. What you might not get right is this question, because we need to figure out where do these MO interactions exist on this diagram. So we want to point to, okay, which one of these lines is A, B, C, and D? So how I want to approach this is I ask myself, is it bonding? So the first question is I want to ask, is it bonding or is it anti-bonding? That's the first question. So this first one, the black dots are our atoms. Bonding orbitals put electron density between the atoms. Is there any electron density between the atoms? No. So is it a bonding or an anti-bonding orbital? Anti-bonding. So I'm going to put a star. I'm going to put a star. It's anti-bonding. What kind of overlap? Squint your eyes and think about, okay, what kind of overlap will result in this molecular orbital? This kind of interaction between atomic orbitals or this kind? Yeah, head on. So what is that called? Sigma. So this is a sigma star molecular orbital. Yay. But we have a problem. Because if you look at our MO diagram you just memorized, there's two sigma stars. There's 2 sigma stars. Oh no. But there's a difference between these sigma stars. There's a difference. This sigma star is between what kind of atomic orbitals? S orbitals. This sigma star is between what kind of orbitals? P orbitals. So A is this one right here. It's not that bad. And the reason A is this one, because if you squint your eyes, you can see that the original atomic orbitals involved here are 2 S orbitals. That's why I know. They just so happen to not be in phase, so they're anti-bonding. Do we have another sigma star interaction in here? Yeah, C. C is also a sigma star, right? That there's a lack of electron density between the 2 atoms. You actually see a node here, so we know it's star. I guess I never got to my second step. We want to say, is it sigma or pi interaction? So is it head on or is it side by side? And then the third one is you want to think about what atomic orbitals are making those MOs. So this is star. We said it's sigma because it's that head on overlap. But then you need to squint your eyes and think what original atomic orbital is making this interaction. Is it an S orbital that's making it? No, it's a P orbital. So that means C, this interaction actually goes at the very top, right here. It's that sigma star. So see how the overlap is similar in that it's a head-on interaction. There's a lack of electron density between the 2 atoms, but the detail is the atomic orbitals that they originate from are different. These are S orbitals. These are P orbitals. So you want to put them in the correct, placement here. All right, so let's keep going. Let's think about this. Is this bonding or anti-bonding? Bonding. What kind of interaction is it? Pi or sigma? Sigma. So it's just sigma regular. Now we have to ask, squint your eyes, what kind of atomic orbitals are making this interaction? 2 p orbitals. So we are right here, right there. Okay, the last one. We have a lack of electron density between the 2 atoms. So what kind of, is it bonding or anti-bonding? Anti, so it's star. So then is this a pi interaction or sigma in nature? This is pi this time. So see how it's way different than these other ones where the node, I guess how it's not head-on overlap. It's more side to side, but still you get a lack of electron density that goes away from the bonds itself. So this is pi star, right? And there's only one place where pi star can be. All right, so it's not like confusing where you could have like sigma. There's 2 sets of sigma and sigma star. This is a pi star. Okay, see, is it that bad? It's not that bad. All right, other question. 20. Yeah, let's just do 27. So question 26 definitely requires a deep understanding of MO theory, how waves combine. All right. 27 is easier in that you don't need, if you don't know those things, you can probably still get this question right, as long as you know how to count electrons. So in this question it says, according to MO theory, which substance has the strongest bond? So for MO theory, there's things we can inspect. We can inspect magnetism, where paramagnetic substances have unpaired electrons. That's paramagnetic. Where diamagnetic substances have paired electrons, everything's paired. It requires you to draw out the entire MO diagram. All of these questions requires you to draw out the entire MO diagram. So we can inspect magnetism. We can also inspect bond order. So how I like to calculate bond order, there, at least in my class, I taught that there are 3 different equations for bond order. For this one, it's one that's specific for MO theory. It's number of bonding electrons minus number of electrons in anti-bonding over 2 is the bond order of your entire molecule. And so if you draw the MO diagram and you calculate the bond order, you can answer this question because bond order trends with strength. It also trends with length. So as bond order increases, how does strength trend? As bond order increases, think about it. Bond order, single bond, double bond, triple bond. Which bond is strongest? A triple bond. So as bond order increases, strength increases, but length decreases. So there's a ton of ways I can ask this question, and it's literally the exact same. In this one, I'm asking which one possesses the strongest bond. So I am asking which one has the highest bond order. But I could also ask which one has the longest bond. Then you would give me the one with what bond order? Lowest. All right. So there's tons of ways we can ask these questions. They're all exactly the same. Requires you to draw the MO diagram. So what you note here is that we have 3 substances. All right. They're all the same except just, you know, cations or anions. So the strategy here is start with the MO diagram for the neutral one first, and then add or remove electrons as necessary to get the other ones and calculate the bond order each time. So which diagram do we use? This one or this one? Left or right? The right one. We use this one because look, it's fluorine. It's not, yeah, so we don't use that one. All right, so remember what these diagrams are. We're looking at the 2s and the 2p interactions. So let's remind ourselves, what is the electron configuration for a fluorine atom? We have helium, 2s2, 2p, 5. So we have 5 valence electrons on a fluorine. But the thing is, how many fluorine atoms do we have? 2 of them. So since each fluorine atom has 7 valence electrons, how many total valence electrons are in a fluorine molecule? 14. So we want to make sure we place 14 electrons in our diagram. So on the outsides, you see we have we can put our 7. These are just for the atomic orbitals. So I'm just basically rewriting the electron configuration. What we want to focus on is in the middle. All right, so we just place the 14 electrons. We're reorganizing them in the middle here, following Aufbau's principle and Hund's rule. So 1, 2, 3, 4, 5, 6, follow Hund's rule. 7, 8, 9, 10, 11, 12, 13, 14. There we go. So just for fun, is this molecule para or diamagnetic? Diamagnetic, very good. All right, so this is my neutral diatomic fluorine. Let's quickly put in the bonding and anti-bonding orbitals because that's going to help us calculate bond order. So we have sigma, sigma star, sigma, pi, pi star, sigma star. So what is the bond order in diatomic fluorine? 14. It's bonding electrons minus anti-bonding electrons over 2. So let's just highlight them. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. 1, 2, 3, 4, 5, 6. So 8 minus 6 over 2. The bond order is 1. Is that consistent with the Lewis structure? Yes, it is, because MO theory is always consistent with those things. Okay. So that's the neutral thing, bond order of 1. So how do we make the MO diagram for the cation? Do we have to start over from scratch? No, we just remove an electron, but which electron do we remove? We remove this anti-bonding electron. So what is the new calculation? We still have the same number of bonding electrons, but we removed an anti-bonding electron. So when you remove an anti-bonding electron, you actually strengthen the bond because anti-bonding, those types of MOs are bond destroying. So if we remove an electron, we remove that destroying nature. But let's recalculate the bond order. I still have 8 bonding electrons, but go through. How many anti-bonding electrons are there now? There's not 6, there's actually 5 now. So 8 minus 5 over 2, the bond order of the cation is 1.5. Because we removed an anti-bonding electron, it strengthens the bond, right? How about the anion? All we do is add an electron to the neutral thing. So we have to go back to the neutral. So if we add an electron, what kind of orbital, MO, does it go into? Sigma star. So if we add an electron to an anti-bonding orbital, do we strengthen or weaken the bond? Weaken. So what we get is when we make the anion, we get a bond order of 0.5. So which one has the strongest bond? The cation. Yes. Which is weird because in like Lewis structures, we usually, the more electrons between the atoms, if we add more electrons to the bond, doesn't it increase the bond order, bond strength? So that's weird. Here, with MO theory, which is the real theory because you're solving the Schrodinger equation, when you add electrons to fluorine, you actually weaken the bond because you're adding the electrons to anti-bonding orbitals. Good. So these questions, there's a multitude of ways to ask them, all right? But they all are the same. You just calculate bond order, you draw the MO diagram, always start with the neutral thing, make the cation or anion. Yeah? 16? Yeah. Oh man, this is the long one. Okay. So this will probably be the last one I do because this one's long. So here, it's funny, we skipped a lot of chapter 8, but that's all the Lewis structures. So I hope you do got Lewis structures down. So let's order these substances in increasing bond enthalpy between sulfur and oxygen. So just like the previous question, right, where we tried to locate the strongest bond, we were looking for the highest bond order. That's the same thing in this question. The strongest bond is going to have the highest bond order. But the difference is this is not MO theory. This is resonance structures. So I like to use a different calculation for bond order, specifically for resonance structures. How I like to describe it is the number of bonds that are involved in resonance over the number of positions or Lewis structures of the double bond is how you calculate bond order. And so I'll just show it. It's easier if I just show it, because this is where we can have fractional bond orders, right? Okay, so SO2. So we need to go through our 6 steps. So I'm going to go through this very quickly, because it's just the 5/16 steps. So SO2 has 18 valence electrons that we need to place. Sulfur is our central atom. So 2 bonds to oxygen. So I've drawn 4 electrons already. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Where do the last 2 electrons go? On the central atom. All right. So now we check octets. Oxygen has a complete octet. This oxygen has a complete octet. Does the sulfur have a complete octet? No. So if I was high school Lisa, I would have just drawn 2 more electrons because I'm dumb. And I don't understand the concept of valence electron money, but we don't do that. How do we complete the octet of sulfur? Yeah, we move a lone pair and make a double bond. So all we're doing, we've already placed the 18 electrons we're allowed to spend. So what we're going to do is just move around electrons so we can make sulfur have a complete octet. So I'm going to move one of the lone pairs to make a double bond to that sulfur. But the idea is, well, okay, so I chose the oxygen on the left, but you might have chosen a different oxygen. Couldn't I just as easily chosen this oxygen or lone pair on the right? And so the idea here is that you can technically choose either, and that's the idea of resonance, that there's multiple ways to complete the Lewis structure. I could have done it this way, or I could have done it, whoops, not that way, this way. I could have done it this way, where the double bond is on the other side. So both of these are completely valid Lewis structures. All of the formal charges are exactly the same for them. It's just what's different is the location of the double bond. So so the big question here is, one of these structures more right than the other? No, it's not. Both of them are right. So is the double bond, are we going to have a short bond and a long bond here? No, we're not. So the idea is that this substance actually undergoes resonance, and we don't see a bond order of 2 and 1. We kind of want to take like the weighted average here. This is where the bond order calculation is. It's the number of bonds involved over the number of positions. So the bond order in this molecule, this is the correct Lewis structure. The bond order is 3/2. So it's 1.5. All right, so it's between that of a single bond and a double bond, because essentially we've just smeared that double bond in 2 places. So that double bond exists on both sides at the same time. So there's our bond order. So we need to do that for all of these. So if we do sulfite, that is 26 valence electrons. So sulfur in the center, a bunch of oxygens. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. So oxygens have all complete octets. Does sulfur have a complete octet? Yes, it does. But the problem is sulfur has a formal charge of 1, 2, 3 plus 1 right now. And that's not preferred, all right? We want to minimize formal charges. So we actually need to form 1 double bond to make sulfite, all right? So the correct Lewis structure is going to have 1 double bond. So for the same reason, does that double bond exist in 1 location? No, it doesn't. It's actually, you could have finished it from any of those oxygens. So the bond order in this molecule, it's not a short bond and 2 long bonds. It's a bond order of 4/3. So it's 1.33. All right. So the idea is formal charges take over here. It's more preferable for sulfur to have a 0 formal charge than and expandix octet than to have a +1 and -2 in the same molecule. A way to kind of your question? Yeah. What? Oh, crap, you're right. Oh, because of formal charges again. Yay. Yes. So I did it for this one, but I didn't do it for that one. Yes. So this one actually also doesn't undergo resonance because of formal charges. So just like why I made a double bond here to reduce formal charges, I do the same thing here. If you calculate the formal charge of sulfur right now, it's +1. Yeah, you're right. I wasn't even looking at my key. We want to reduce the formal charge of that central sulfur atom. So that sulfur will actually have 2 double bonds. It will expand its octet rather than have a formal charge of +1. That's not preferred. Because if you calculate the formal charges of everything, there's a 0, there's a +1, there's a -1, and that's not preferred. So instead, if we draw it this way, it's all 0. And that's good. Yes. So sorry about that. So the bond order here is 2. Because there's no resonance. Yeah. So does this molecule undergo resonance? No, it's just 2 double bonds. Okay. So there we go. So here's their bond order for sulfite is 1.33. So let's do sulfate real quick. So I think there's how many valence electrons? I don't know, 30 something. How many? There, thank you, 32 valence electrons. So sulfur, do you want me to answer this question or not? Okay, thank you. So sulfur in the middle, 4 oxygens, so 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So in this example, we don't need to put any additional electrons on that on the sulfur atom because we run out of electrons. But the problem is that sulfur right now as drawn has a formal charge of +2. So we want to make 2 more double bonds. 2 more double bonds. And doing so will reduce the formal charge of sulfur back to 0, which is preferred. So 2 double bonds. So the idea is I just chose those 2 double bonds, those oxygens, but you could choose any 2 oxygens to form the double bonds. So are those 2 double bonds localized on these 2 bonds? No, they're not. The 2 double bonds are essentially smeared across the entire molecule. So the bond order for this molecule where sulfur has 2 double bonds and 2 single bonds is 6/4. I like to count how many bonds total. So like 2 double bonds. So 1, 2, 3, 4, 5, 6. 6 total bonds involved in resonance over 4 different unique resonance structures that I could draw. So that's what 6/4. So sulfur oxygen has a bond order of 1.5 here. So finally, we can answer the question, which one has the strongest bond? The first one, the second one, or the third one? The first one. So these questions are tough because you have to draw all of the Lewis structures and consider their resonance in order to answer them. So for the rest of them, just please look at my keys. Good luck.